So welcome everyone, and again in this video we are going to talk about periodic Sturm Liouville boundary value problem. Okay, so in the last video we talked about regular Sturm Liouville boundary value problem, right? This is also a similar sort of thing, a little different. Okay, and let me define the what I mean by this problem. So basically again we have the same equation. So consider the problem. What is the problem? It is py prime whole prime plus qy plus lambda ry equals to 0. Yeah. So this is the problem which we have. If you remember, we are assuming p q r to be c1. You don't need it to be, but let's just do it. It's not a problem. And p and r we will assume it to be positive in whatever the domain is, alpha beta, let's say in the interval which we are talking about, alpha beta. Yes, and the boundary data, and in this case you see what we are going to do is a little different. Since we are talking about periodic Sturm Liouville boundary value problem, okay, what we will do is we will take p of a equals to p of b. Okay, this is the condition on p. Along with p and r positive, p is sufficiently smooth, p has to be equals to will be equal at ab means this is ab. Let me just put it in a comma b, ab. Is it okay? And what is the boundary condition? The boundary condition is given by this: y at the point a equals to y at the point b, y prime at the point A equals to y prime at the point B. So you see, it's a beautiful condition, right? Basically saying that y and y prime at the point A is basically the same with y and y prime at the point B. So basically ya equals to yb, y prime A equals to y prime B. Yes, the position and the speed of the particle, let's say at the point A, yes, is same as the position and the speed of the particle at the point B. That's what it is saying. So basically it is coming back to this original configuration somehow. So that is this sort of problem is called periodic Sturm Liouville boundary value problem. Okay. So what I am going to do is start by working out a problem, and then we'll look at some properties. Yes. Okay. So the first problem what we have is this. See, let's say this equation is there. So for the question is this: for lambda in R, okay, solve this equation. Solve y double prime plus lambda y equals to 0. Yes, and periodic conditions, right? So see, p equals to 1 here. It's p equals p at the point A and p at the point B is same basically. So y at the point 0 equals to y at the point pi, and y prime at the point 0 is y prime at the point pi, right? That's your periodic condition. Yes. Now we want to solve this problem. Yes. What do you do? So first of all, case 1. Again, why I chose lambda to be r? Here the question is lambda to be r. You do not have to worry about c, right? Now, of course, you can think of c and all, but the thing is, again, we will prove our theorem, which will actually guarantee, like the last video we talked about, right? There also we have shown that the eigenvalues are going to be real. Here also the same sort of thing will happen. So you really do not want to worry about that. Okay, right? So what is the case 1? Case 1 is let lambda is 0. Okay, lambda 0 case. So in that case, y double prime equals to 0, and the solution that will imply what is y of x. The general solution will look like c1 times x plus c2, right? Now you see y0 equals to y pi. So basically c1 times 0 plus c2 equals to c1 times pi plus c2, right? So what does it give you? C2 is C1 pi plus C2. So that will give you C1 has to be 0. There is no other option. Okay. So that will give you C1 is 0. Now if C1 is 0, y prime at the point A equals to y prime at the B. What is y prime? Y prime now y of x, let's say, will look like C2 of C2. Y prime should be only C2, right? C2. Now that will satisfy y prime of 0 equals to y prime at the point pi, because it's a constant. Y prime is 0, so basically 0 function at the point 0, 0 function at the point pi is basically 0, right? So it's satisfied. So what are the eigenvalues in this case? So basically in that case it is basically any arbitrary eigenvalue, so it's one eigenfunction. Okay, so we can think of it as 1. You can take any other number, it's not about non-zero constant, basically you can take. So thus we can say that 0 is an eigenfunction, okay, and what is the eigenvalue, and the corresponding eigenvalue is basically any non-zero constant, and the corresponding eigenvalue is any non-zero constant. Is it okay? Yes. So simple, right? Okay. Let's look at case 2. What is the case 2? Case 2 is let lambda is negative. Yes. So if lambda is negative, then lambda equals to minus mu square, we can write it, right? And mu is real and non-zero. Is it okay? Now if that is the case, then what's the general solution? Therefore the general solution is given by yx equals to, okay, so yx in this case looks like e power c1 times e power mu x plus c2 times e to the power minus mu x, right? And c1 c2 is in R. Yeah. Now given those boundary data, so please check this part. This is easy, so I am not doing this time. So the boundary data, if you incorporate it, that will imply c1 equals to c2 equals to 0. Is it okay? And hence what do you have? Yes. So the only solution is a trivial solution in this case, yeah. And hence what happens is there are no negative eigenvalues. There are no negative eigenvalues. Is it okay? Right. Okay. So now let's look at this. What happens if it is there are positive eigenvalues? So case 3. So let lambda positive. Okay. Then what do you have? Lambda is mu square. Okay. Mu is real and non-zero. Is it okay? And what is the general solution? The general solution is given by yx equals to some constant c1 times cosine mu x plus c2 times sine of mu x. Is it okay? Now y satisfies the boundary data. So y satisfies the boundary data. If and only if, when is it satisfies? Y0 equals to y pi. Okay. So y0 equals to y pi will give us a sine mu pi, okay, plus b 1 minus cosine mu pi is equals to 0. And we will also get a y prime 0 equals to y prime of pi. The rows will be reversed. Okay. So a 1 minus cosine mu pi, okay, minus b sine mu pi is 0. These are the two which we are going to get, right? Now this system, let's call this system as 1. Now the system 1, okay, admits a non-trivial solution. I want it to admit non-trivial solution, otherwise there are no non-trivial solutions basically. Okay, sorry, what am I writing? What is AB? This is C1, C2, C2, C1. Yeah? So the system admits non-trivial solution. Non-trivial solution if the determinant, what is the determinant? Sine of mu pi 1 minus cosine mu pi and 1 minus cosine mu pi minus sine of mu pi, this is going to be 0. Yeah, that will imply that cosine of mu pi has to be equals to 1. That will imply that mu has to be equals to plus minus 2n. Is it okay? So n is in n. Yes. So what is lambda? Therefore lambda has to be equals to 4n square. Yes. N is in n. N is in n. Yes. So what are the eigenvalues? The positive eigenvalues. Therefore the positive eigenvalues are 4n square. Okay. N is in n. And the corresponding eigenfunctions and the corresponding eigenfunctions are let's say phi n of x is sine of 2nx and phi n of x is cosine of 2nx. Is it okay? Yes. See, the thing is, this has a non-trivial solution. Okay. So there is a non-trivial set C1, C2. Both are not simultaneously 0. That is okay. Such that this equation has there is a non-trivial solution. So basically, in that case, what is the solution? Either it is sine and cosine. Okay. So basically, if you put C1 to be 0, C2 to be 1. So you have sine, and then for C1 to be 1, C2 to be 0, you have cosine, right? So basically you have two linearly independent eigenfunctions for each eigenvalue. Yes. You see, the motivation behind giving you this particular how do I put it, example is the following. In this example, what we have seen is this: for let's say 4n square is an eigenvalue for some n, right? In whatever it is, 5, 10, whatever. Now you get two eigenfunctions, sine of 2nx and cosine of 2nx. And we know that sine of 2nx and cosine of 2nx, these two are linearly independent. Yes. So for each eigenfunction, you are going to get two linearly independent eigenvalue. That actually says that this eigenfunction. So that actually says that this basically that eigenfunction 4n square is not simple. Yes. But for a regular Sturm Liouville boundary problem, we have seen that these sort of eigenvalues are always simple. Yes, simple. But in this case, it is not going to be simple. Yeah. So this is one major difference between regular and periodic Sturm Liouville boundary value problem. Let me make a small remark here. Yes. Remark. The eigenvalues of a periodic Sturm Liouville boundary value problem are not real. Sorry, what am I saying? They are not real and are not simple. They are real, they are real, but they are not simple. Okay. Now the thing is, why they are real, that is also we need to understand. So basically what I am going to do is this: I am going to write down a theorem with the two parts. Okay. So the thing is, the eigenvalues of star, this equation star, the original equation. What is the equation? Yeah. So this is, let's call this star. Okay. The eigenvalue star, if any are real. Okay, so basically they are not simple, but they are going to be real. Yes, what is the proof? You use the exact same sort of proof we did for regular Sturm Liouville boundary value problem. Only you remember, you just use that the boundary data is basically different. Use that fact, the boundary data is different, right? Use that boundary data and you show that they are going to be real. Exactly the same sort of proof works, just a little tweak is required. I hope you can do it yourself. So this whole theorem is for you to check. Okay, right? And the thing is, I proved another theorem, right? Okay, the second part, the second theorem. So what about that orthogonal thing? Yes, so that also holds here. So what is the theorem? The theorem says the eigenfunctions, okay, of a periodic Sturm Liouville boundary value problem, periodic Sturm Liouville boundary value problem, okay, corresponding to distinct eigenvalues are orthogonal with respect to R in AB. Is it okay? So basically what I am trying to say is this. See, there are basic 3 theorems which we prove. The properties, yeah, other than the existence, 3 theorems which we proved for the regular Sturm Liouville boundary value problem. The first one is the eigenvalues are going to be real. If they exist, they are real. So that holds for both regular and periodic. Yes. Okay. What about the orthogonality of distinct? So basically, let's say you have 2 distinct eigenvalues corresponding to that 2 distinct eigenfunctions. Yes. You can actually show that they are going to be orthogonal. You can show it for the regular or the periodic Sturm Liouville boundary value problem. Okay. Now, what about the other property, whether they are simple or not? This is, with this example we have shown that this is not true for periodic Sturm Liouville boundary value problem. Is it okay? Right. Now, another this thing theorem which we want to do. So this is about that theorem, existence theorem. Very, very important. Again, this is, again, we are not going to prove this theorem. If you want, you can just look it up in the Coddington book. Okay, so what does the theorem say? So basically, periodic Sturm Liouville boundary value problem, okay, has an infinite sequence of eigenvalues. Okay, you see, you remember for periodic regular Sturm Liouville boundary value problem also we showed that there are like an infinite sequence of eigenvalues. Okay, here also the same thing, lambda n is in n. Okay, satisfying this particular property. So basically, you know that monotonicity property is also satisfied here. So basically, minus infinity, you can actually show that this goes on doing this thing. Lambda 1 is less than lambda 2. Yes. So there are at least 2 there, and then they may repeat themselves. So less than equal lambda 3, less than equal lambda n, less than equal, this goes on. And now the thing is, the first eigenvalue lambda 1 is simple. Okay, this is always true. The first eigenvalue lambda 1 is going to be simple. Okay, and the number of linear, and the number of linearly independent Li, okay, eigenfunctions corresponding to any eigenvalue mu, okay, is equals to the number, okay, of times of times mu is repeated in the above listing. See, this is different here. You remember, if you think about it, for the regular Sturm Liouville boundary value problem, this is like distinct: lambda 1 less than lambda less than lambda 2, which is less than lambda 3, which is less than lambda 4. It goes on like this, such that lambda s goes to infinity. That's what it was given there in the regular Sturm Liouville boundary value problem. Okay. In this case, however, what happens is this, and what happens is lambda s goes to infinity also. You remember, lambda s goes to infinity. For the periodic Sturm Liouville boundary value problem, you don't say something like that. What you can say is, of course, there is a lambda 1, which is of course greater than minus infinity, and which is strictly less than lambda 2. That is there, that we know. But after lambda 2, it can be all the same. You know, everything is lambda 2, lambda 2, lambda 2. It will go on like this. Yeah. And if it happens, so basically you see, they may, they may recur itself. So lambda 2 can be twice, thrice, 5 times. Okay, that can happen. Okay, now the thing is, what you can say is this. Let's say mu is there. Yeah, mu is any one of them. Lambda I something. Yeah, mu. And corresponding to that mu, let's say mu is actually repeated 10 times in this scheme. Yeah. So mu is 10 times repeated. Then what happens is the number of eigenvalues, linearly independent eigenvalues corresponding to that mu will be 10. Is it okay? So basically they are going to be same. How many times it is repeated? Yes. So here also you see what is the eigenvalue. You see here the eigenvalue is 4n square. In this is a periodic Sturm Liouville boundary value problem, right? In this problem the eigenvalue is 4n square. Yeah. And this is repeated twice. So basically there are the eigenvalues are basically 2. So basically 4n square, right? Okay. So the thing is, how many linearly independent eigenvectors should be there corresponding to this 4n square eigenvalue? So it will be sine nx cosine nx. So basically it is 2. You see, it is, since it is this actually in the scheme, if you think about it, it is coming twice. So that is why there are like 2 linearly independent eigenvalues. Is it okay? Okay, so that is there. Now the thing is, I will finish this particular video with the problem which I want you guys to do it yourself. Okay, so let's look at an exercise. This is for you to do it. Y double prime plus lambda y equals to 0. Okay, y at the point pi equals to y at the point minus pi, and y prime at the point pi equals to y prime at the point minus pi. Okay, so this, what you want you to do is find the eigenvalues and eigenvectors. Okay, right. So with this I am going to end this video.